Quantum entanglement is a fascinating and complex phenomenon in quantum mechanics where two or more particles become linked in such a way that the state of one particle instantaneously influences the state of the other, no matter how far apart they are. Imagine this. You and a friend each have a pair of magical dice that are entangled. No matter where you roll your dice, even if you're on opposite sides of the planet, if you get a 6, your friend's dice will instantaneously show a 6 too. This is entanglement in a nutshell. So how does entanglement actually work? First, we have the creation of entangled particles. Entanglement often begins when a pair of particles, such as photons or electrons, are generated from a common source or interact in such a way that their quantum states cannot be described independently of each other. Once entangled, the properties of these particles, like spin, polarization, or momentum, become correlated. If you measure one of the entangled particles, you'll find that the other particle's corresponding property will match in a predictable way, even if they are separated by large distances. Before measurement, each entangled particle exists in a state of superposition, meaning it simultaneously possesses all possible states. Upon measurement, the particle chooses a state, and due to entanglement, the other particle will choose a corresponding state instantaneously. This instantaneous correlation has been famously described by Einstein as spooky action at a distance, because it seems to defy the classical understanding that nothing can travel faster than the speed of light. Yet entanglement appears to involve instantaneous communication between particles. Some have suggested that entangled particles might have predetermined states that are revealed upon measurement, but experiments have shown that this is not the case. The particles truly do influence each other's states at the moment of measurement. But what practical applications arise from this quantum magic? Here are some of the key applications. Quantum key distribution, QKD, uses entangled particles to securely distribute encryption keys. If an eavesdropper tries to intercept the key, the entangled state would be disturbed and the intrusion would be detected. Quantum computing harnesses entanglement to allow quantum bits, qubits, to be in multiple states simultaneously, leading to exponential increases in computing power for certain tasks. In the field of medical imaging, quantum entanglement can enhance techniques for optical sensing and high-resolution radio frequency detection, improving the clarity and detail of medical scans. Entangled particles can also improve the accuracy of GPS systems by enhancing the precision of atomic clocks, which are crucial for GPS. While teleportation of matter as seen in science fiction is not yet a reality, quantum teleportation, transmitting the state of a particle to another particle, is a developing field. Superdense coding is a related concept that could potentially increase the capacity of communication channels. Beyond QKD, entanglement is used in various protocols of quantum cryptography, which could lead to virtually unhackable communication systems. Now let's dive into one of its most fascinating applications, quantum teleportation. Quantum teleportation is a process that allows the transfer of quantum information from one particle to another over a distance, without the physical transmission of the actual particle itself. Here's a step-by-step explanation of how it typically works. First, it all begins with two particles are entangled, meaning their quantum states are linked together regardless of the distance between them. Next comes a third particle, which holds the quantum information or state to be teleported, is prepared. This particle is not entangled with the other two. The third particle is measured in conjunction with one of the entangled particles. This measurement changes the state of the entangled particles due to the phenomenon of quantum entanglement. The outcome of this measurement is sent to the location of the second entangled particle through classical communication channels. This is the only part of the process that is not instantaneous and is limited by the speed of light. Finally, using the information received, the state of the third particle is reconstructed onto the second entangled particle. This step effectively teleports the quantum state of the third particle to the second entangled particle. But what are the limitations of quantum teleportation? While groundbreaking, it comes with several challenges. Quantum teleportation requires classical communication to send the results of measurements from the sender to the receiver. This means that teleportation cannot occur faster than the speed of light, as the classical information is bound by this speed limit. The current technology does not guarantee a 100% success rate for teleportation. For instance, certain protocols may only succeed in a fraction of attempts due to the specific quantum states involved. While there have been successful experiments teleporting quantum information over long distances, such as using the Mikia satellite over 1,200 kilometers, the energy extracted is limited by the distance between the sender and receiver. The upper bound of the energy is inversely proportional to the distance, which poses a challenge for long-distance quantum teleportation. There hasn't been a quantum teleportation system yet whose rate can reach the order of hertz. This limits the practicality for applications like the quantum internet, where a higher rate of teleportation would be necessary. Quantum teleportation requires entangled particles, which are resources that are not only difficult to produce, but also need to be maintained. The process of maintaining entanglement over time and distance is resource-intensive and technically challenging. The fidelity of teleportation, which refers to the accuracy of the quantum state that is reconstructed at the destination, can be affected by various factors, including environmental noise and imperfections in the entanglement. High-fidelity teleportation is crucial for practical applications. As we continue to push the boundaries of quantum mechanics, the dream of instant communication and teleportation inches closer to reality. Stay tuned as we unravel more mysteries of the quantum world. Until next time, keep questioning the nature of reality.